Okay, I'm going to give a specific example of how you would use node voltage analysis on a particular circuit configuration. So there's several steps we're going to go through, and the first one is, first of all, we need to find our reference node. So we need to set our reference node. And I'm just going to choose this bottom node because remember all of these parts along here are connected by wires, so there's no components changing them, or there's no components between them, so they're all connected, they're all the same node. And this fulfills the criteria that we have for reference nodes, which is one, we want that reference node to be at the base of a voltage source, which we have. It's at the base of the 12-volt voltage source. And we want it to be connected to as many components as possible so that we can minimize the number of unknowns that we have. So our reference node I'm going to set at the bottom. Now I'm going to go through and I'm going to name some parts of our circuit here. So the first thing is I'm going to name the nodes. I'm going to call this node A. This node is node B. This one is node C. This node is node D. And then we've got this one, and that's E. And we know that VE has to be equal to 0 because that's our reference node. But we also know that node A, it's at the top of the 12-volt source, so it has to be 12 volts higher than node E. So node A is equal to 12 volts. Okay, so now really we've only got 3 nodes that we don't know the voltages of. Okay, I'm going to add a couple other things here. So this, I'm going to call whoops, got a little excited there with my plus signs. This I'm going to call V1. The voltage drop across that resistor is V1. The voltage drop across this resistor is V2. This one will be V3. This one will be V4. We have V5. And then this one will be V6. Excuse me. Now the last thing I'm going to do is I'm going to put my currents in there. And I'm going to assume, if I think about this, what's going to happen is the current is going to come out of that 12-volt voltage source. It's going to pass through node A and resistor 1. And I'm going to call this I1. Okay. Now when I1 hits point B, it's going to split into 2 currents. And I'm going to call this one I2. That's going to go down to our reference node. And this one I'll call I3. And when I2 hits the reference node, then it basically kind of circulates back into the battery, so we're not going to worry about that. I3 is going to pass through resistor 3 into node C, and at that point, that is going to split. We'll call this I4 and this I5. Now, I'm not going to do the same thing at node D, because basically I5 is going to pass into node D, and then it has to pass through resistor 6. Because it's only connected to 2 components, whatever goes into it has to be the same thing that comes out of it. And so we don't need to worry about creating separate currents for node D. All right, so now what we're going to do is we're going to write our equations using KCL. Now this sounds like a very easy step, but it's a little bit longer than we anticipate. So we're going to start with saying that, we're going to start looking at node B because we're going to have to use this on nodes B, C, and D because we don't know the node voltages there. Okay, so starting with B. Well, the current going into B is I1, and I2 is coming out, and then I3 is also coming out. So that's our KCL equation. Now, that'd be great, except we don't really know anything about the currents. So what we're going to do is rewrite it in terms of our voltages, which we can write in terms of our node voltages, and our resistors, because we know our resistors, right? So we remember that Ohm's law says that V is equal to IR, and therefore our current will be equal to the voltage over the resistance. And so we can rewrite this as V1 over 9 kiloohms, I'm going to put R1, minus V2 over 6 kiloohms, oops, I should probably stick with one convention or the other, R2 minus V3 over R3, and that has to all be equal to 0. So that's basically the same equation as this rewritten. Now, unfortunately, that's still not useful because we're looking for the node voltages. We can figure out what V1, V2, and V3 are as long as we have the node voltages. So we're going to rewrite this equation in terms of our node voltages. So that's going to be, and then I'm also going to insert my resistor values. So it's going to be VA minus VB over 9 kiloohms. Okay, so that part kind of makes sense. We're basically saying that there's a current passing from A to B and that it passes over, sort of through a 9 kiloohm resistor, and that's basically what I1 is, okay? Now, one thing is, when I do my currents, I tend to make them go into the node that I'm writing the equation for, and the reason I do that is so that I don't mess up on my signs. If I assume that all of the currents are going into the node, and I do that for all three, whatever you do for one node, you should do for the rest of them, because otherwise if you start flipping things around, that's where you run into problems. So I pretend that all of the currents are always going into the node I'm writing the equation for, okay? So that means that for V2, the way I'm going to write that is, well, I'm going to start at VE, which is 0, and then I'm going to go into B, all right? And that's over 6 kiloohms. And then I do the same thing for the last resistor. I say that the current has to be flowing from VC to VB, and that's over R3, which is a 3 kiloohm resistor. And all of that has to be equal to 0. Okay? So, now the way I do this, and there are other ways to do this, and I'm going to show you on the next equation another way of doing this, is I try to find the common denominator, the least common denominator, and then I multiply times that. So the least common denominator here, well, we've got, this one's 3 squared, this one's 2 times 3, and this one's 3. So our least common denominator is going to be 2 times 3 squared, which is 18 kilovolts. Sorry, kiloohms. So what I'm going to do, just to make my life easier, is I'm going to multiply this whole equation by 18 kiloohms. What that leaves me with is my first term, my 18 kiloohms will be divided by 9 kiloohms, which will leave me with a 2. So I'll have 2 VA minus 2 VB. In the second term, 18 kiloohms divided by 6 kiloohms leaves me with a 3, so I'll have minus 3 VB. And the last one, 18 kiloohms divided by 3 kiloohms leaves me with 6, so I'll have plus 6 VC minus 6 VB. That all equals 0. I gather my like terms to VA, so then when we look at VB, that's going to be minus 2, minus 3, minus 6, so that's going to be minus 11 VB, and then plus 6 VC. That all equals 0. And this we're going to call equation 1. Okay? So that's our first equation. That's the equation that we got for VB. Okay? All right. Now, one thing I should make one change really quick. This is not equation 1. We're getting to equation 1. VA, we found out, was 12 volts, right? So I'm actually going to plug that in to simplify this equation. And equation 1 will actually be 11 VB plus 6 VC is equal to minus 24 volts. Now you'll notice everything in this equation is in volts, okay? So that's our first equation. Now I'm going to show you another way of doing this. We're going to write the equations for C and D. So I'm going to start with node C. Okay. and if we scroll back up and we look, node C has I3 coming in and I4 and I5 leaving. So the equation for that is going to be I3 minus I4 minus I5. And again, that equals 0 because we're looking at KCL. One thing that we can do is we can kind of rethink of our resistors as something called conductances. Okay, so we can rewrite this and we can say that our conductance G3, for instance, is actually 1 over R3. And we can write our equation that way. This is just another way of doing it. I'm just going to show you this as a side note. So what we can do is we can say, well, I3, if you look back at the circuit, I3 basically is passing from node B to node C, so that's B to C, through resistor 3, right? So we can say that rather than taking it through, we can say it's 1 over R3. So I'm going to do that for all of these. I4, if you look at the circuit again, that's going to be, if we again go with our current going into, is coming from ground. I4 is coming from ground, passing through resistor 4 and going to C. Well, actually the negative of I4. But since we're treating it as something that always goes in, just for mathematical purposes, we're going to say that this is plus VE, which is 0, minus VC. Oops. Sorry, I shouldn't do it that way. 0 minus VC, but it's passing through resistor 4, so I'm going to say 1 over R4. Okay. And then the last one, if we scroll up again, that's going to be I5. Remember, we're treating all the currents as going into node C, so we're going to go VD minus VC times 1 over R5. Now, why would I do this? Because I can rewrite R3, R4, and R5 as conductances. So the conductance G3 will be equal to 1 over R3. G4 will be equal to 1 over R4. And G5 will be equal to 1 over R5. Okay, so when I rewrite my equation, what I get is VB minus VC times G3 minus VC times G4 plus VD minus VC times G5. So if I rearrange things, I'm going to get VB G3 minus VC times G3 plus G4 plus G5, then plus VD times G5, and that equals 0. Now, why would I do this? Because if I go through and I calculate it out, G3 is something like 0.00033 repeating. G5 is 0.0001 repeating, and G4 is 0.00025. Those are messier numbers to deal with. They're not whole numbers. But writing it in this way can make it easier to use a computer. Because what you can do is you can basically say, I have my variables R1, R2, R3. You can set those as givens in your computer program, and then you can determine your equations, and then when you go in, you can also set G1 as being 1 over R1, G2 is 1 over R2, etc. And you can just program those in as givens in your computer. And that makes it a lot easier if you want to use a computer to solve this. So we aren't going to do this right at the moment. I just wanted to show you that this was one way you could do it, because I'm going to recommend that you try this problem out using all three methods I'm going to show you to solve problems or discuss. Okay, so go back to node C. We're going to rewrite this equation, but we're going to do it in a way that's useful. Now, the other thing I want to mention is when you solve these equations, you should always make sure that all your equations have the same units. So the first equation, everything was in volts, right? We canceled out all of our resistances, so everything's left in volts. If you take this equation, you actually have a current here, because a voltage times a conductance is a current. Because remember, it's the same thing as taking a voltage and dividing by a resistance. So you can't use the equation 1 that we had before and this equation, because they have different units. You have to make sure they're all the same type of equation. Okay, so back to equation 2. I'm going to find it in volts now. Okay. Oh, the other thing I wanted to mention about doing it this way is that power is equal to voltage time conductance squared. So again, if you know your voltage drop across the nodes, or the voltage drop across the resistor, you can just take it times the conductance squared. So that's another way to find power. Okay, so back to equation 2. So I'm going to say VB, I'm going to rewrite it in terms of my node voltages and my resistances instead of the conductances. This is the equation that I get when I assume that all of the currents are flowing into the node at VC. That is, I'm assuming VC is at a lower potential than all the other surrounding nodes. And I look, my common denominator, well, this is 3, this is 2 squared, this is 3 squared, so my common denominator is going to be 2 squared times 3 squared, so that's 4 times 9, which is 36 kiloohms. So I'm going to multiply the whole equation by 36 kiloohms. That's going to give me 12 times VB minus VC minus VC times 9, because 36 divided by 4 is 9. And then 36 divided by 9 is 4, so I'm going to have plus 4 times VD minus VC. I'm going to rearrange and combine like terms. So that gives me 12 VB, and then we're going to have minus 12, minus 9, which is minus 21, minus 4, so we've got minus 25 VC, and then the last term is plus 4 VD, and that's equal to 0. Okay, this is equation 2. And now we're going to do one more equation for the last one, which is VD. I'm going to scroll all the way up here. So this one, what we've got is we've got I5 passing into it through R5, and then passing out of it through R6. But again, just to be consistent so I don't screw up, I'm going to assume that both voltage or both currents going through R5 and R6 are going into VD, so that I'm using that as my as the one that I'm subtracting off. Okay. So to write that equation, I'm going to write VC minus VD over 9 kiloohms. Okay. And then plus 0, which is VE, minus VD over 3 kiloohms. Okay. My common denominator here is 3 squared, which is 9. So I'm going to multiply all the terms by 9 kiloohms. That's going to give me VC minus VD minus 3 VD equals 0. Combine like terms, I get VC minus 4 VD is equal to 0. And this is our equation 3. Okay, so now we have 3 equations and 3 unknowns. Our first equation that we had was minus 11 VB plus 6 VC, and that's equal to 24 volts. Our second equation is 12 VB minus 25 VC plus 4 VD, and that's equal to 0. This should be D. And then the last equation is VC minus 4VD equals to 0. Okay, now what can we do? Well, there's 3 different ways to solve this. The first 2 are do it by hand. In the first one, we just use straight substitution. The way I would do this, substitution. I would basically solve equation 1 and 3 for VC. I would substitute that into the second equation, into equation 2. So once you have equation 1 and equation 3 in terms of VC, that means you've got VB and VD in terms of VC. You can plug that into your second equation. Your second equation will only have terms of VC then. You can solve for VC. And then once you have VC, you can plug it back into equations 1 and 3 to get VB and VD. Then once you have all 3 of the node voltages, C, B, and D, you can use that, and you can use Ohm's law, and you can solve for any any current through the circuit or any voltage drop across any of the resistors. Okay. The second way you can do this for small values is you can, well, you can't use too big an equation, but if you are sufficiently competent using Gaussian elimination, you can change into matrices and use Gaussian elimination. I can't spell today. Elimination. Okay, so what would that look like? Well, you're going to have minus 11, 12, 0, 6, minus 25, 1, 0, 4, minus 4, and those, of course, will give you your V1, V2, and V3, and then you can have your 24, 0, and 0. Now, there's a couple ways you can do this. If you use your conductances, you can just use the conductance values instead, in which case your right-hand side will be currents instead of voltages. And then you can either use Gaussian elimination. Sometimes you can solve in matrix form. If the matrices are small, you can use things like Cramer's rule and stuff like that. And then the third way, kind of built on this, is use MATLAB. So if you're familiar with using matrices from MATLAB, you can go in and you can use this. You can use the idea that AX equals B, except in this case, usually you have a form of GB equals I. You can solve for this by saying that V is equal to I. Whoops. Better make sure I write my formulas correct. G inverse I. And then you can use your matrix manipulations in MATLAB. Okay? So I'd recommend you giving a try and doing it all 3 ways. Okay? If you end up with 3 or more nodes, it's almost always easier to use MATLAB. When I give you exams and things like that, chances are this would be the biggest kind of problem I'd give you, and it wouldn't have too many unknowns. So just keep that in mind. But I would suggest trying this problem in MATLAB and doing it by hand and checking it.